In this lecture, we're going to learn how to determine an equivalent force for a distributed load. So we can replace the distributed loading with one single force. And after this class, you should be able to solve a problem looks like this. So we have a bundle of boards stored on the storage rack. And this lumber places a distributed load with a loading intensity. So we call this as the loading intensity, load per unit length, on the beam holding the bunk. To analyze the load's effect on the steel beams down here, it is often helpful to reduce this distributed load to a single force, or to replace this distributed load with a single force. And that's the topic in this class. How do we find this equivalent force to replace the distributed load? Let's use a simpler and familiar example to understand sometimes a body may be subjected to a loading that is distributed over its surface or body, but we can replace it with one simple load to have the equivalent effect. For example, this pile of sand. And we know that its total weight is distributed through the pile because this pile of sand is made up of individual sand grain, and each sand grain has a weight. But usually we do not use those distributed load, right, the dW. Instead, we replace the distributed load with one concentrated load, W. And to replace it, and to place it at the centroid of the body, or the center of the body. And to make sure this weight, W, has the same effect as the distributed load, dWs, it needs to satisfy two conditions. First, this weight, the magnitude, is equal to the resultant force of the distributed load. Second, W must be properly positioned in order to have the same moment with respect to any point as the distributed load. Again, force has two effects. One is translational motion, one is rotational motion. We have to make sure this weight you used to replace the distributed load will have the same effect, including the translational motion, which is the resultant force, and the rotational motion, which is the moment. As that being said, the goal in this class is to find two quantities. First is to find a force, or the resultant force, which is equal to the sum of all the distributed loads. Second is to find the location of this force, x bar. Where should we position it? To figure out the magnitude of that concentrated load Fr and the location of it, let's look at this piece of board resting on the ground. It has a length of L and width of B, and this surface is defined as the XY plane on the floor. And now there is a distributed loading acting on the board along the x direction. And we use pressure P as the distributed load. And we know P pressure is force per unit area. So the unit is Newton per meter squared, or Pascal. And this pressure is not a constant pressure. Instead, it's a function of position x. So again, pressure is force per square per meter squared, or force per unit area. And that is the pressure, and pressure is a variable. It changes with x-axis, or is a function of x. So you can see now at x equals 0, the pressure is higher, while when x equal to L at the end of the board, the pressure drops, is smaller. But we can express the relation between the pressure and location using a function of x. Let's take a look along the y direction. Along the y direction, the pressure follows a uniform distribution, which means the pressure profile is the same across the width of the board, or into the board. Now, this will refers to as simple distributed load, which means the load only varies along one direction, usually the x direction, and it doesn't change along the other direction, like the y direction here. Now let's choose one differential area on this board. So if we choose one differential area at any arbitrary location x, and this differential area has a different differential length dx along the x direction, and the width of it is b. So this dA, the differential area, is dA equals to b times dx, where b is a constant value, which is the width of the entire board. Now, based on the definition of pressure, pressure equals to F over A, and since force is a variable, so we're going to use the differential form, which will be dF over dA, and we can replace dA by b times dx. And then we can rewrite this equation by moving the value b to the other side of the equation. So we will have dF over dx, force per unit length, equals to b, the width of the board, times px, the pressure, the distribution of the pressure. So now we have force over length instead of force over area. So we're going to give this term a name, which is called the load intensity, and we use the symbol W. And W, the load intensity, is also a function of x because it's equals to b times px. So it's still a function of x, and it represents the sum of the pressure along the entire width b. Again, along at location x, right? Each point has a pressure px. So when you add them together, the entire length is b. B times force per unit length will be the overall force over that length. So the unit of it, based on the unit of the unit pressure is Newton per meter squared, force per unit area, and times the length, which will have the unit meter in the SI unit system. So load intensity will be Newton per meter. Again, it is the force per unit length. By defining this load intensity function Wx, we can then reduce a 3D problem. So x, y direction, including this force applied in the z direction, that's a 3D problem. But we can replace the 3D problem to a 2D problem by removing the y-axis. Since everything across the y direction is the same, is a constant. So we can use this plane to representing any plane along the y direction. So now this problem becomes a 2D problem, and for the x-axis is the length along the board, and the y-axis is the load intensity with the unit Newton per meter. Now let's calculate the resultant force and the resultant moment from the distributed load, or the sum of the forces and sum of the moment from the distributed load. First, let's take a look at the magnitude of the resultant force, because we know the direction of this force field pointing down, so we'll just consider the magnitude for now. To find the overall force, let's consider a differential length dx. This dx is any dx or differential length dx located at an arbitrary location x. Since Wx, the loading intensity, is defined as dF over dx, force over length, then the total force over this length dx, which is dF, should be equal to, or we just rewrite that equation, right? Should be equal to the intensity, loading intensity times the length dx. And if we take a look at this differential area, the area, shaded area here, which has the width of dx and has the height of wx, because when we choose this differential length dx, here is one point located on this curve, and this curve is described by the relation between x and wx, right? At position x, the y value is wx, is given by this relation described by the curve. So that means if we bring out this differential area, you have dx over here, and you have wx over here. So dx times wx actually is the area under this curve, or the differential area under this curve. So the total force would be sum of all the differential forms, and when we have an unlimited number of elements, when we add them together, that means we're going to integral them. So the overall force, or the total force, the resultant force of the distributed load, equals to the integral of the differential force dF, and which is actually the area under the curve. So that's actually the meaning of integral. Or to write one more step is the integral of W, the loading intensity, times dx. And keep in mind, the loading intensity is a function of x. So then now we know the net force on this beam is given by the integral of loading intensity times dx, which is actually the area under the curve. And it means that if we want to replace this entire distributed load with one single load, and this load should have the same magnitude as the sum of the entire distributed load, which means this force must be equal to the integral of the loading intensity dx, or it must be equal to the area of the curve, or area under this curve. Next, let's take a look at where should we place this force so it will create the same moment as the distributed load. Let's first figure out what is the resultant moment from the distributed load, and then the force should have the same moment about the same reference point. So again, to find the resultant moment, we still need to use the differential moment created by this differential force. So this differential force dF is applied at a location x, distance away from the point O. So we're going to find the moment about this point O. So the moment arm of this differential force dF equals to x, and therefore the differential moment let's define counterclockwise rotation as the positive moment. So this d of MO should be equal to, now since the df is to the right of this point O, so it will create the clockwise rotation. So it will be a negative moment. Moment arm is x, and this force, magnitude of the force is df. So this is the differential moment, or the moment caused by this differential force df located at location x. So the resultant moment will be the sum of all the differential moment. In other words, this moment about point O by the distributed load equals to the integral of this dmo. So x times df actually has a negative sign. This is our dmo. We just figured out. And to plug in this df, the differential force is the differential area, which will be the loading intensity times dx. So replace dx by wx times dx, or replace df by wx times dx. Then this is the result we have. That means the total moment about point O because of this distributed load equals to the integral of x times wx times dx, and it's clockwise rotation. So if we're going to replace this distributed load with one single force, this force should also create the same moment about this point O. So let's take a look at this resultant force. So we just got the magnitude of this resultant force, right? The magnitude of the resultant force equals to the integral over L loading intensity times dx, right? So we assume this force should be located at a location x bar, so it will create the same moment about point O as the distributed load. So now, if the FR is located at x bar, the moment of FR about point O is negative. Again, counterclockwise rotation will be positive. Is negative moment arm x bar, magnitude of force FR, moment arm times force. And we replace this FR by the integral of wx dx, which we got earlier here. Okay, so equation 1 is the resultant force from the distributed load. Equation 2 is the moment of this resultant force, or of this single force. So for this force FR to have the same rotational effect about point O, those two moments should be the same. After re-equating that two equations, equation 1 and equation 2, the moment about point O, we can get this relation, or we can calculate or figure out the location of this single concentrated load, where we use x bar as the location of this concentrated load, and it equals to the integral of x times wx dx, which is this equation is the moment about point O gotten from the distributed load, and the bottom is the FR, the force. Moment divided by force is the moment arm. In this case, this moment arm is the location of this concentrated load. And this coordinate x bar locates at the geometry center or centroid of the area under the distributed loading. And the resultant force has a line of action which passes through this centroid Z of the area under the loading diagram. And this is the equation to find the x bar, the location of the concentrated force that will be used to replace the distributed load. So we can use the integral method to find the centroid of any area, but in this class, for the most of the time, we're going to solve some special areas or special cases which you don't have to use the integral method. So here's one example. When the load intensity has a uniform distribution across the length of the member. In other words, this loading intensity is a constant value, doesn't change with the x-axis, and this distributed load has a rectangular shape. And in this case, the resultant force, Fr, equals to the area of the rectangle, and the location of this resultant force is just half of the length, half of L, which means it passes the centroid of this area, or the centroid is just in the middle of this geometry. Second case is when the load intensity function Wx follows a linear distribution. It's a straight line varying from a value W0 to 0 across the length of the board. In other words, the distribution of this loading intensity forms a triangle shape. So again, the resultant force is the area of the triangle, which is the half of W0 times L, and the location of the Fr is in the geometry center, which is 1/3 from the base. So this is the base, 1/3 from the base, or 1/3 from the axis indicating the loading intensity.